Welcome to our departmental seminar at the Informatics department. Today we're very excited to host Professor Aggelos Kiayias from the University of Edinburgh. Aggelos requires a little introduction in the space. Nevertheless, let me say some words. He's the chair in cybersecurity and privacy and the director of the blockchain laboratory at the University of Edinburgh. He's also the chief scientist at the company Input Output that supports the Cardano blockchain. His research interests and contributions are in the broader area of cryptography, applied cryptography, foundations of cryptography. He has received numerous fundings, numerous grants, and numerous distinctions. I think the most recent one was the British Community Society Lovelace Medal yesterday. So he is a co-recipient of that medal for 2024. And it's, I can continue with many accolades, but it's our great pleasure to have him here. So Agil, the floor is yours.
Thank you very much. Yeah, thank you, Anna. Thank you for being here, and thanks for everybody for joining the call, joining the meeting online. The talk, the title is Ouroboros Lessons Learned and Key Challenges in Blockchain Protocol Design. Ouroboros is a blockchain protocol that I led the design of, perhaps now already almost 10 years ago, when we had our first, we were working on this problem, and there were a number of developments that happened since, which I will review in this talk. But first, I'm going to start with one of the main motivations for these questions, or for the type of questions that we will cover in this talk, which is the consensus problem. So this is one of these beautiful, jewels type of problems in computer science. It has a very simple, natural definition, and as it so happens, with great problems that exist in computer science and mathematics has a simple way to define, but it turns out that it's a very interesting and intricate problem to solve. So the consensus problem asks for the design of a protocol. So parties have to exchange messages, and each one of them has an input, and they're going to produce some output. And the high-level requirements is that all the parties have to terminate, they have to produce an output, and very importantly, they have to agree on that output. And at the same time, what is called validity says that whatever they agree on should have some relation to what is their input, right? So validity is here is essential because validity and agreement are given termination of the two fundamental properties. Achieving each one of them by its own is trivial. For example, if I just output 0, all the parties would agree. But of course, that would not be very useful because it has no connection to what is the input that we have. Right? So there is the main reason that this problem is difficult is that not all the parties necessarily follow the protocol. So that's what makes it challenging. If all the parties follow the protocol and the network communication is easy, is good, then there's no problem. Nevertheless, what is the challenge is that we would like to solve this problem in this so-called Byzantine setting. So this is one of the strongest settings that people have considered for the problem. But basically says a certain number of the parties, let's say 2 of them, they diverge from the protocol in some way that we don't know. They can diverge in a coordinated manner, so they're all controlled, let's say, by the same adversary. And the challenge, of course, is that we would like to make sure that the other parties that do follow the protocol, they agree and they have all the properties that we just said. They terminate and their output satisfies validity. In this classic definition of distributed systems literature, the parties that follow the protocol, they're called honest. The parties that do not follow the protocol are called malicious. and there is no attempt to understand why they're honest, why the honest parties are honest, and why the malicious parties are malicious. This is just given. This is just a given, right? We just accept that. And the question is, what can we do under with these circumstances? As we will see, this is an assumption that we would like to revisit, and this is actually one of the reasons for a lot of research. One of the motivations of a lot of research work in the consensus problem. Now, in the last few decades, but especially given the advances in the Bitcoin blockchain, there's a new variable. There's another variable of the problem called ledger consensus. So what I defined before as consensus is, you can think of it as a one-shot problem. Like, we have an input, we want to produce an output, done. But there's this other variant of the problem, which is, you can think of it as an ever-going protocol. Like, inputs come, and we want to organize the inputs in a log. So you can think of it as a log of transactions. I mean, that's a way to understand that. So this relates to the state machine replication problem, which has been studied, of course, also early on, a bit after the consensus problem I mentioned. The high-level requirements are consistency and liveness. Intuitively, consistency means that the logs of the honest parties, maybe they're not identical, but the only reason they're not identical is that the one might be a prefix of another. So that's the only reason that you don't get agreement, right? So, and you can think of it that that's a natural relaxation, because in a network that is not perfect, it's just impossible to absolutely everybody have the log to be exactly at the same depth, right? So it could be the case that, let's say, my log could be falling a bit behind than your log, and then it's catching up as messages are delivered. So we're happy to allow for this small disagreement if you want, but this is like a small degree of disagreement, right? It's just a prefix of another. And you can think of consistency as a type of agreement property, but the property also would be trivially satisfied if we never put anything in the log. So it's one of those things, right? So in order to make sure that the log is also meaningful, we have this other property called liveness, and there's a few different variations, but I'm going to use this. I'm going to refer to liveness as a property that says, as time passes, transactions that are submitted to the nodes of this protocol, they are incorporated into the log. Perhaps with a wait time, right? So there's going to be a wait time. So it's not, I mean, we accept the fact that even if a transaction is sent to everybody, maybe some time is going to pass. And during that time window, perhaps messages will be exchanged, and then eventually everybody's going to put the transaction into the log. So that's the variance of this. Of this consensus problem that motivates a lot of the work that I'll talk about. Now, a classical solution to this problem came with this quite influential paper called Practical Byzantine Fault Tolerance that put together a lot of the understanding that people had on consensus and showed how you can actually design these protocols in a way that it's practical. I mean, sufficiently practical to have it implemented and realized. So, and in many ways, this defined the way people were thinking about this problem. There's like highlights here with, for instance, saying that this is an asynchronous protocol like the internet. So the internet was thought as a network communication, like an asynchronous place. And asynchrony was essential in achieving the properties that the protocol was striving to achieve in terms of consistency and liveness. So some of the characteristics was that it was asynchronous communication. The operation was safety favoring. So when things were going bad, safety was upheld and liveness was given up. Right, so this means basically that consistency was always maintained. You never lost consistency, but maybe liveness was, given up. So in other words, if the network was not sending messages or something was going wrong in the network, you wouldn't do progress. And the general setting was an authenticated one, so every party that was running the protocol could authenticate the messages from the other parties, and that's very essential. So the number of participants was fixed, and there was a computational bounded adversary in the sense that digital signatures were used in the protocol and the adversary was not able to force them. There was a setup assumption, which in cryptography sometimes this is referred to as a public key infrastructure, or a PKI, basically a list of keys. There was an upper bound on how many participants are controlled by the adversary. That was 1/3 of the total. And the communication complexity was rather high. So it was like quadratic in the best case, and could be worse in certain executions of the protocol, depending on how things were going in the protocol. So now I'm highlighting this high communication complexity, because this also describes a bit the number of participants that this can scale to. So clearly, you could imagine that this would work for, I don't know, 10 or 20 servers, but you wouldn't say reasonably expect that this would work for, I don't know, thousands, let's say, servers, right? Because of the complexity of the protocol. Now, it's interesting to now contrast this with the Bitcoin protocol, which solves actually the same problem. So, of course, it talks the Bitcoin blockchain, the Bitcoin protocol talks about payments and transactions and digital assets, but we can move all that to the side for a moment and think of the Bitcoin blockchain protocol as a consensus engine. And if you look at it from that perspective, it does solve the same problem as this one. It's a ledger consensus protocol. But it does solve it in a different setting. And actually, what is very interesting about it is that it runs over the internet uninterruptedly since 2009, but it doesn't assume an asynchronous communication network. So it actually, Bitcoin only as a protocol, it only makes sense in a bounded delay setting. So basically in a setting where delays are bounded. So from a technical, from a computer science perspective, from a protocol design perspective, it's very intriguing now to compare the two, because this one emphasizes that the internet is an asynchronous environment, and that's why we're designing it in that setting. But the Bitcoin protocol, which clearly runs well over the internet for so many years, it's not operating in this setting at all. In contrast, it operates in a bounded delay setting. So just highlighting some of the properties of the Bitcoin protocol. It's also a ledger consensus protocol, but it does assume communication with bounded delays. You can prove actually the protocol breaks in the asynchronous setting, like it wouldn't work. It has a liveness favoring operation. So in other words, where things are bad, and I'm not actually fully defining what bad means, but just take this sentence, let's say, as at face value for the moment. But when things are bad, the protocol is liveness favoring. So in other words, the protocol will keep processing transactions, but you will not, it will sacrifice safety. So it could be the case, let's say, just to give an example, in a network split, you could have two versions of the Bitcoin blockchain operating in parallel, and then when the network is joined again into a one unit, you would have one of these two chains, like basically becoming the dominant one, and the other one being abandoned. This is actually how it works by design. And actually, this relates to this property of the protocol, which is called the self-healing property. So the Bitcoin blockchain has a self-healing property, which I will spend some more time in a moment. But some other characteristics which are interesting and very different from the classical setting is that it operates in this unauthenticated setting. So it doesn't require public keys or a PKI for the consensus part. Just to be clear, for those of you that know the Bitcoin blockchain, you will remember that it does use public keys, obviously, and this is for the ownership of Bitcoin itself. But this has nothing to do with the consensus part. So the consensus part of the protocol, it does not need the public keys, at least in terms of agreement. So
So you get this no need to authenticate the servers, and contrast the next line with the fixed number of participants in the classical protocols. Here we have an unknown and fluctuating number of participants. Now, in the literature, this has been termed as dynamic availability in the recent literature. So the number of participants that is alive and running the protocol at any given time is not known, cannot be predicted. I mean, it is assumed to be not radically different from 1 second to the next. So it's not like in 1 second there is like 5 people running the protocol and then 1 billion people running the protocol. So it's not like such a sharp differential between one step to the next. But, you know, the protocol is completely comfortable by saying that, you know, today the number of participants is like this, but let's say, you know, some short amount of time in the future, the number of participants has changed a lot. Protocol has no problem with that. And it has some other properties, like it has privacy for maintainers, which is not the case for the classical protocol. But very importantly, in terms of communication, the protocol is amazingly communication efficient. In other words, just to be clear how to understand that, so per block of transactions, or if you think like a block of transaction is the basic unit that we would like to measure these protocols for, because these are constructing a log, right? So you can think of the basic unit that we can measure is a block of transactions that goes into the log, right? And the log is, you know, contains this sequence of blocks. So the amortized communication complexity is a single multicast per block. So in other words, for every block of transaction, you just have to multicast that block in an amortized sense. That's remarkably small amortized communication complexity compared to the quadratic one that we had before. And by multicast, what I mean by multicast here, essentially I mean big O of n, right? So multicast means like, well, I mean, you have to send this thing to everybody, but that's it. You know, in an amortized sense, that's all you need to do. So if you want to measure this in somehow classical complexity terms, this is like somehow a linear overhead in an amortized sense compared to quadratic and worse in the classical protocols. So the Bitcoin protocol is really communication efficient, and that's one of its characteristics. So when the Bitcoin protocol appeared, the thread model, what I'm describing here, was basically an unexplored territory for transactions. So nobody had, you know, considered that particular configuration, right? So furthermore, and that made things more difficult, was that the thread model I'm describing here was not spelled out anywhere. So it's not like the Bitcoin white paper said, oh, I'm going to present a consensus protocol that has this particular. It was presented in a completely different way, right? It was kind of the use case driven. Basically, it said this is about payments, digital currency, exchanging money on the internet. It was not highlighting somehow these features here, which you can think these are more of a way to understand the Bitcoin blockchain, looking at it from the lens of consensus protocols, like in the academic literature, right? And that's not the way it was presented. I mean, Bitcoin was not presented as an academic paper, and it was not, well, you know, peer-reviewed in the sense that you would get peer-reviewed other research papers. So I'm going to highlight a bit the dynamic availability and the self-healing aspects. Now, the dynamic availability turns out to be the key feature which is different from the classical result. So it turns out that this dynamic availability requires the bounded delay. So, and now you can see where one of the main tensions is going to come into. So these classic protocols, they don't work with dynamic availability. They basically have a fixed number of participants, so they know how many people are there, and that's why they can operate in an asynchronous setting as well. And the reason is that you know how many people are there, so once you hear from a sufficient number of people, like you can say, okay, I mean, I have an understanding about, you know, what to do, right? But that's the main difference with the Bitcoin setting. So the Bitcoin setting needs the bounded delays because it has no clue actually, you know, the number of participants, and it doesn't try to predict or use the number of participants. So it has to use bounded delays. And that's something that now we can formally prove. So it's a way, it's possible, I mean, to define a formal model that describes what dynamic availability is and prove that this requires bounded delay. So you cannot reconcile full asynchrony with dynamic availability. Another aspect, which I'll highlight, is that the adversarial spikes basically mean that there are moments where the number of malicious participants may exceed the honest ones. And that's actually a pretty bad thing for classical consensus. We know that classical consensus needs honest majority, otherwise we cannot solve it. And this actually sort of spike situation is not a good one for these protocols. So the question is how to achieve it and what would be the impact of that. And an outcome here is that we cannot finalize the ledger. So the ledger or the log is never finalized, because what basically Bitcoin does is that it gives you a log, and you, as the user of the log, you can say, I believe it or not, based on some risk assessment that you personally can do. So that's not something that the protocol does. It's like you listen to what is out there as a user, and you can say, I can make a risk assessment based on my belief about the network, and then I can choose to believe or not what is the settled part of that log. And the more conservative you are, the more you may have to wait for the log for time to pass. And that's exactly what happens in Bitcoin. So that's another very atypical setting that is characteristic of Bitcoin. So just to give you a sort of a toy visualization, so you can think of dynamic availability as something like this, where the number of honest participants in blue and malicious participants in red change over time, and they can double, triple, or take, or even go up, or even go down, and the spike, you can visualize it as something like this. So there are moments where the number of malicious participants exceed the number of honest participants. Now, in the one-shot consensus case, that's not a very, there's probably nothing you can do in that territory. But you understand, because here we're solving ledger consensus, which is a protocol that doesn't terminate, it just goes on forever. It's legitimate to ask, because this x-axis here is time. So you can say, okay, I have a spike here. I mean, things maybe are bad here. Maybe transactions are, not finalized, or maybe transactions are censored. Okay, I mean, bad things are happening here. There's no way to avoid that. But you can ask the question, what about a transaction that was processed here? Does the fact that I have a spike here affects this transaction there? Or you can ask about the transaction here. Would the protocol ever recover from this? In other words, yes, you had a spike here, but would you be able, let's say, later on, to go to this healing stage where everything is back to normal? Or just the fact that you had a spike here, like, spoils things forever? Now, these are not straightforward answers from a protocol design perspective. So it turns out Bitcoin is very good at doing both. But again, this was again an unexplored territory for ledger consensus protocols. So people that looked at protocol design were not trying to answer these questions, at least from the example.
Can I ask a question?
Yeah, please do. Yeah.
Did you merge? So we have like honest nodes, but we also have like honest nodes that are faulty, right?
Mm-hmm.
Do you consider them an adversary in this setting? So do we still?
Yeah, you can take various approaches with this. So, the most simplistic way is you can say, everybody who is somewhat faulty, I'm throwing them into the Byzantine pile, and then the rest is honest and all good. So that's an approach you could take. And the nice thing about the Byzantine analysis is that it allows you to do this. So in other words, you can say, some are malicious, some are faulty, and just clumping them all together and I say that's the adversary. Now, is this the best thing to do under all circumstances? Not necessarily. Actually, you might try to do another approach and say, I'm going to have some nodes which are honest, but they just like fail stop, so they kind of fail and start. and there are other nodes with just malicious. So that's actually a better approach, so it can give you a more fine-grained analysis, and this is what has been happening in a lot of recent papers, including my papers in the space. So we distinguish between parties that stop and start. In other words, they go to sleep, for instance, you can say, and then they are activated again. And you can even think that their activation schedule could be adversarially driven. So the adversary can go and say, now you go, now you stop, now you go, now you stop. And you can start then asking, how many of those guys do you need to be active at any given time? So that's the model of this dynamic availability, where you have two classes of parties. But you can take this point further, and you can think of other cases as well. You can think of like parties that are corrupted, let's say, they have to lose their secret keys, and then, I don't know, they try to recover and clean up afterwards. So there's a lot of options here. Yeah, and I think, like, you know, there are ways to extend these models in a number of directions. Now you might ask now, okay, so this is a new setting for consensus, but is this just an academic oddity? I mean, do we care about this? Is that, I mean, yes, okay, you can take any protocol problem and you can tweak this or that, and you can say, is that something I care about? And now I would say, okay, you can say I care about because that's Bitcoin, and I don't know, Bitcoin is cool, but this is like a very specific angle of looking at this. So now I'm going to give you another way that you could care about it from a basic computer science perspective, and this has nothing to do with digital assets or anything else. So that's my motivating use case, which I call it the software-only launch problem that does a bottom-up system launch. So software-only launch says the following. And now you can forget everything I said so far. Just doesn't matter. Everything I said so far is not relevant. You can just focus on understanding this. So I'm telling you that this is your project. Maybe let's say that's your semester project. The semester project is that pick some IT service, anything you like. For example, I don't know, you would like to build a new social network. Yeah, that's what you like to do. Or you would like some database that's public and does, I don't know, like, you know, manages traffic, like who knows, you know, whatever. Like you have some IT project in mind. No, just pick one you like. And I say the following. Your task is certain like time down the line. Let's say 6 months, without saying if that's realistic or not. So 6 months down the line, I want the system to be running. So basically, there should be a way somewhere out there that I could download some software and engage with that system that you had in mind. And now, in order for you to launch the system, you are restricted in the following sense. You can only write the software, and you can make it public, but you cannot run the software yourself or convince anyone else to run the software. So the only thing that you can do is like write the software and release it. And then somehow, for whatever reason, I mean, you have designed it perhaps in some certain way, the software itself will make its own case. So people will just sit and say, yes, I want to run it. And then by people running it, the service will be created like because people are running it. So you have to make it so that the software should be written in such a way so that it will sell itself. So now I want you just to understand that this is not the way, not the typical way that you would launch an IT service, right? This is not the way, let's say, Facebook or Google or, you know, or Amazon became great, you know. They became great because they had great ideas, but then they made companies. The companies like, you know, bought servers, and they wrote the software and they put it on the server. They have customer support, like, you know, they just created the whole system, and it's still running on their system. So you are constrained with all that. You cannot do, the only thing you can do is like do a software-only launch. You only write the software. Maybe you can write a blog post about it. Okay, that's fine. And then you can just put it out there. So, and people will run it. So that's a very, very strange way to create an IT system in a completely bottom-up fashion. For some reason, the people like see the software and say, oh, that's cool, I want to run it. And the Bitcoin blockchain was not the only system in history that did this. So there are some early precursors of this software-only launch. And you can think of them as some precursors of this in the form of the peer-to-peer torrent networks of the end of 90s and beginning of 2000s, where basically also bottom-up people were running them because they wanted to run. They wanted to run the software. In other words, there was a utility, it was a positive utility for the participants that's saying that I'm downloading this, putting computational resources I have into running the software, and then I'm getting something out of it. But I think it will be a very easy case to make, without making it too formal, that what Bitcoin achieved is way more remarkable than any of these early examples. So the system is remarkably stable, predictable, like every 10 minutes. Like there is a Bitcoin block that processes transaction on average, right? So every 10 minutes on average this happens. And this has been happening the last 15 years or 16 years, and it's happening essentially in an uninterrupted fashion. So that's not something, so the resilience of the Bitcoin network is nowhere near, like it's at such high level that you cannot put it at the same level in these early systems, even though the Bitcoin blockchain, definitely if you look at its design of its protocol stack, it gained a lot of understanding and knowledge about how to organize itself from these early peer-to-peer networking protocols. So, perhaps another aspect that I should highlight here is that here we're also thinking of software itself, or if you want even cryptographic software, if you think cryptography is essential, but it's like software that in itself is a mechanism that incentivizes the participants to engage with the system. And the system, whatever the system wants to do, is sort of a side effect of their desire, of their self-interest and rational choice to run the software. So they make a rational choice to run that software, and then a side effect of that is that the system is created. So that's, I would say, a remarkable feature of the Bitcoin blockchain, and it's something that now you can somehow abstract away what you know about, I don't know, cryptocurrency, I mean, and say like, well, this is something that tells you how to launch information technology services without actually having any specific proponent aside software itself, right? So you don't have a company, let's say, that sits behind Bitcoin and says, oh, we have to do this, right? That's not needed. So to drive the point a bit closer to what I've been doing, briefly, so after the Bitcoin blockchain was created, there was a lot of concern was around the fact that the Bitcoin blockchain is a very inefficient protocol. In a way, it was believed and thought that a lot of its inefficiencies are intrinsic for all its properties. So all the properties that we described was exactly because of this proof of work mechanism that consumes energy, and it's essential. But what came with the proof of stake was a question: could we retain as many of the properties, as many of the threat model and characteristics of the Bitcoin blockchain, but just do away with the energy inefficiency, just do the protocol in a very cost-efficient manner? And in particular, is it possible to keep things like dynamic availability or spikes, self-healing, like all these aspects I mentioned, can we retain them? And it turns out that we could, but we have to also give up something. So what the proof of stake gambit, let's say, does is that it sacrifices something, it makes a sacrifice and says, because Bitcoin operates in a pretty remarkable, you might call entirely permissionless, open, transparent setting. Even at the time of its setup, it doesn't need any private setup, as we say in cryptography. So a private setup is a setup that you can think of like an initial block of data that you put on your server when you run it. So Bitcoin doesn't need this setup to be private. So there's no private data there at all. So the only thing that Bitcoin is a public reference string, as sometimes it's called. For example, the Bitcoin blockchain itself, it used the Times newspaper headline back of January 2009 to launch, that was its public reference string. And it needs that. It needs that reference string. If you don't have that reference string, you cannot argue that the protocol is resilient against pre-computation attacks. So in other words, it could be possible that someone does a huge pre-computation, the protocol starts, and then this huge pre-computation of proof of work comes and destroys the protocol. So you need some, for the Bitcoin blockchain, right, specifically, you need that setup, but it's a public setup, right? So there's no hidden data behind it. So the proof of stake gambit says, okay, let's give up on that. We're going to have some private data needed at the beginning, so we're going to try to handle that. But as long as we handle it well, everything else we would like to keep. So dynamic availability, spike, self-healing, and so forth. And there's a lot of benefits here. Aside energy efficiency, the nice thing is that maybe we could port back a lot of this Byzantine fault tolerance, these BFT techniques that we know from decades of research, because we're going to have back public keys into digital signatures and things like that could go back in, and we could perhaps benefit from that. And there's a lot of benefits. I don't have the time now to discuss them, but we can talk about it later if there is interest in time. So. Now you might ask, okay, we changed it a lot. Is it still interesting? Is there still here a problem that is interesting? And I'll give you this as a motivational use case, which I call the key airdrop launch. So while Bitcoin, let's say, does the software only launch, where basically just software is enough, and the public reference string, but because it's public, I'm not even counting it. The proof of stake suggests this key airdrop launch. So basically it says, let's do the following software launch. I'm just going to throw some public keys, perhaps in the air. Like, maybe they fall, like, you just hire an airplane and, you airdrop them, over the city. All right. You could do something as, extreme as that. Or you can do something more targeted. You could say, I put this public secret keys as QR codes, in the entrance of the building, and then everybody gets a flyer and they have a key, So you figure out some mechanism for massive, key drop, what sometimes people call like an key airdrop, and then under certain assumption that you've organized things so that it's rational for the majority of those. For some majority, most of the people that are going to get your airdrop, by the way, they would say, what kind of garbage is this? I'm not going to care, right? And that's the tricky part, right? So you cannot use a classical BFT protocol to do this, right? Because in the classical BFT protocol, you need to know the number of participants. And if you're doing such a massive airdrop, dropping like, a million such keys, you have no clue where they're falling, right? So it could be like, nobody, they're just, hundreds and thousands of them could fall in the wrong place, and nobody cares. So you have no control of this. But let's say you assume that of those who care, you still have some good percentage. In other words, there's still like some sufficient percentage that cares enough based on, they actually read the thing, then can we do it? And it turns out that we can, and that's exactly the proof of stake setting. So I would say I'm not going to go further into more details in this, but if you are interested in this perspective of looking at these blockchain systems as systems that can organize information technology in this decentralized, let's say, sense, you can check this position paper that I have here, I wrote a couple of years ago. All right, so coming now to explain the title. So a lot of my work was in the design of the Ouroboros protocol, which basically draw this parallel between the Bitcoin blockchain and this setting of proof of stake blockchain protocols that retain all the properties of the Bitcoin protocol, like dynamic availability, self-healing, and others which I haven't highlighted, like privacy and so forth. But they do this in a highly efficient manner. So basically, you don't need to have this energy expenditure by making this adjustment in how you set it up, right? So there is a difference with the Bitcoin blockchain exactly at the setup phase. You have this private setup versus a public setup, but other than that, we retain all the other properties. And this has been something that I've been working on for a number of years, which covers like different properties. So there's different sort of milestones like dynamic availability or self-healing, as well as other more specific things, which I think in the interest of time I'm not gonna go deeply into that. I'm making here a comparison between the protocols. I'm not going to go into sort of the details here, as I'd like to, I don't know, check with Stefanos as well. Like time-wise, finishing in 5 minutes. Is that good? So we have about 5 minutes.
I don't but else if we need a couple more minutes, it should be fine.
Yeah, I mean we can. I'll try to finish in the next 5 minutes, and then we can take questions. Yeah. So perhaps like I should point out one of the key distinctions. I'm not going to, in the interest of time, go too much into the details, but there is a difference in the corruption model. So in cryptography, there is a lot of interest in understanding the adaptivity of the adversary in protocol design, which basically means that when you have the adversary, can the adversary make decisions about what parties to take over and corrupt, in other words, take control of their resources, and can they do that, can the adversary do that as the protocol evolves. So I see how the protocol goes, and adaptively I make a decision and say, okay, I want to take over that particular entity. So the Bitcoin protocol has a purely adaptive operation, but there is in the proof of stake setting we have to make certain discounts, and this continues to be a very interesting and active area of research as we speak. So for instance, in the proof of stake setting, like in the Ordoros Prowse paper, we have this adaptive model with erasures. So an adaptive model with erasures basically says that we can tolerate adaptive adversaries provided that the nodes themselves have the ability to erase memory. And erasing memory, I mean, as some of you may know from cybersecurity, is an assumption you can make. You can say I have it here and I erase it, but it's not necessarily like an easy task. So, for instance, because of fault tolerance, you can have like many copies of memory at any given time. So different version, the key could find itself in different locations. So, so making sure that we can get security without erasures is an interesting question. I'm not going to go to the details I mean, I have a lot of more other stuff here which I won't cover. Maybe I'll just give a quick nudge on the issue of decentralization itself. So there is a perhaps I'll just stick to that slide. So decentralization is the feature of these protocols being executed by multiple different parties that are independent. And independent is the key point. So because they operate in this permissionless setting, you have no controls of how the parties organize themselves. So it could be the case that the parties just run the protocol individually without cooperating with each other. But it could be the case that they cooperate with each other and they create one virtual party, all of them together, that runs the protocol. And this actually is a problem because these protocols get some of their security profile or security characteristic exactly by the fact that multiple independent parties run the protocol together. So if all of the parties create a virtual party that essentially then is delegated to one entity, you can run into a situation where you have a single point of failure that an attacker now can target and take the whole protocol. So measuring the actual decentralization of real systems is a project that we are currently running at Edinburgh University, and we have what we call EDI, the Edinburgh Decentralization Index. I'm going to describe all the details that I'm saying here about measurements we have done with live systems, including Bitcoin and Ethereum, but if you're interested to understand more about what decentralization is and how you can measure it, I would welcome you to check this QR code, which will bring you to our website. And you can learn about different metrics of decentralization, including the one that's mentioned here, the Nakamoto coefficient. I mean, given the time, I'll just skip it. I'll also skip many of the challenges, and maybe I'm just going to go to some of the lessons learned, and I'm not even going to cover everything. But I think like a major highlight here is that reverse engineering the Bitcoin threat model has been very rewarding from a academic consensus protocol design perspective. So it's shedding a lot of new light in the consensus modeling landscape. So we learned quite a lot about the consensus protocol, consensus problem itself by studying this protocol. And then I'll just highlight some of the other elements here which I learned going along the way. For instance, in the second bullet highlights the issue of the network. In many cases, in classical cryptographic and distributed protocol design, the network itself is frequently thought as a black box. So you just say, oh, it's a network, message goes, message comes. But it's not the case at all in this protocol. So the network itself, exactly because it's an open peer-to-peer environment, is a quite complex protocol instance on its own right, and is a one that is not possible to make it, to treat it as a black box. You have to actually think about the network itself in tandem with the higher level consensus protocol as well. And that's one of the lessons I learned. And finally, something about technology transfer. A lot of my work also was about taking these protocols and realizing them so that they actually run in the wild with true participants, and realizing cryptographic protocols is very hard. It's one thing to have the protocol in pseudocode in a paper or in a spec, and another thing to have it actually implemented. And one of the things I learned is that this engineering of this protocol is a huge effort, that once you mobilize it to a certain direction, it's very hard to say, okay, now, I thought about it better, we have to go maybe the other way slightly. It's very difficult. So when you design such protocols, thinking very hard about how do you update them while they run is a very interesting research question on its own right. So having updatability of cryptographic protocols, which is already a highly recognized area in cryptography and protocol design, but also I would say is one that is not sufficiently researched. So sometimes people also refer to this as cryptographic agility. This is a very interesting domain for research, and it's a one that we still haven't done enough. So I have to say I only scratched the sort of surface of a lot of the topics that I had here, but I'm going to be happy to discuss a little bit further as I have time after the talk, and I'm happy also to share the slides and some of the papers I'm referencing here. But I'll finish here so that we are on time. Okay, thank you very much for your attention.